Electric field is a physical quantity that produces force on other charges. This force is coulombic in nature. So, it depends on the distance as well as the quantity of the charges. A charge produces an electric field around it. When a test charge comes in this field, it experiences a force as per Coulomb's law. The electric field produced by the charge Q point at a distance r is given by ER is equal to 1 by 4 pi epsilon naught into Q by r squared into r cap. Let us try and understand the nature of this electric field with the example of the explosion of a bomb. When a bomb explodes, it has a specific radius of impact. Within this radius, everything gets damaged. But if one is out of this radius, one doesn't get affected. If the objects within this radius are considered as charges, then we can say that they are affected due to the explosion. This area is known as the field, and analogous to this is an electric field where the affected objects are electric charges and the explosion or the source is a source of charge. Now that we have a general idea about an electric field, let us investigate its nature. The electric field produced due to a positive charge points away from the charge. The field strength decreases with increasing distance. We can see here that there is a positive charge at the center and the arrows are coming out of the positive charge. The electric field produced by this charge Q at a point R is given by ER is equal to 1 by 4 pi epsilon naught into Q by R squared into R cap. On the other hand, the electric field produced by a negative charge points towards that charge. In other words, it can be shown by arrows moving into the charge from all the sides. Here also, the field strength decreases with increasing distance. But what exactly does a field mean? The word field explains how a quantity which is distributed varies with the position. The electric field reduces at a rate of 1 by r squared. The test charge Q also exerts a force on the charge Q. Now Fr is equal to Q into ER, and the unit of electric field is Newton per Coulomb. The electric field due to a charge Q depends on the distance r from it. So as the electric field exists at each point in space, we can carve out a sphere with a fixed distance r, keeping Q at its center. The electric field at all points on the surface of this sphere will be the same. This shows the spherical symmetry. The electric field due to a charge capital Q at a point in space may be defined as the force that a unit positive charge would experience if placed at that point. To avoid capital Q to move due to the field of small q, we will take Q to be negligibly small. Hence, E is equal to the limit of F by Q. The force F on the charge small q due to the charge capital Q depends upon the location of small q in the field due to capital Q. Moreover, the value of the field due to capital Q is dependent on the distance r from the charge Q. So, if we move the charge at different points in this field, we will get different values of electric field. Hence, it shows that the field exists at all the points in the three-dimensional space. Electric field due to a system of charges. Consider a system of charges Q1, Q2 till Qn with position vectors r1, r2 till rn with respect to an origin O. The charges here are all shown by red dots, and their position vectors are indicated by using dotted lines. Their individual electric fields are also shown here using blue lines. Electric field at a point due to a system of charges is the vector sum of the electric fields at the point due to individual charges. Electric field at a point in space due to a system of charges is defined as the force experienced by a unit test charge placed at that point without disturbing the original position of the charges q1, q2 till qn. Coulomb's law and superposition principle help in determining the charge at point P denoted by the position vector r. By the superposition principle, the electric field E at r due to the system of charges is ER, which is equal to E1r plus E2r till ENR. Therefore, ER is equal to 1 by 4 pi epsilon naught into Q1 by R1p squared into R1p cap plus 1 by 4 pi epsilon naught into Q2 by R2p squared into R2p cap till 1 by 4 pi epsilon naught Qn by Rnp squared into Rnp cap. This can be written in a short form as ER is equal to 1 by 4 pi epsilon naught summation of Qi by Rip squared into Rip cap from I equal to 1 to n. Physical significance of electric field. Calculation of electric field is of tremendous importance due to the technological applications of electric forces. To determine the trajectories of electrons in a TV tube, in an accelerator used in cancer radiotherapy, or of charged particles in a semiconductor electronic device, we need to know the detailed nature of the electric field acting on the charges. Thus, electrical field helps us to determine the environment of an electric charge. Let us understand one such application. Here we have a cathode ray tube. It consists of an electron gun and two sets of deflection plates present inside the casing. The electron gun emits an electron beam and it passes through the deflection plates onto the screen. This electron beam is bent by applying different voltages across the two sets of deflection plates. The electric field between these plates is responsible for the deflection of the beam. All this leads to the formation of some specific pattern on the screen.